Welcome students, let me continue our next chapter, that is what limits and derivatives. That is in continuation the 12th topic, and this is the first topic in the unit calculus here. This is the only topic that you are studying this year. Actually, this calculus is studied in detail. More of the concepts are studied in the next year, that too for second PUC. See, in this calculus, you are mainly concerned with the study of functions. And then you are mainly concerned with the limits, and then continuity, the concept of continuity, and then again there is another very important concept, that is what differentiability or differentiation here, differentiation, and then integration, their application part. Still many more concepts are there in the unit calculus here, and it mainly deals with the study of change in the value of a function as the points in the domain change here. If you take into consideration the function, say y is equal to f of x. See, in this case, here x is independent variable, means any value you can substitute here, it is independent variable, whereas y is a dependent variable. The value of y depends on the value of x. That's why y is a dependent variable and x is independent variable here. So that is what it mainly deals with, the study of change in the value of the function, change in the value of this function y as the points in the domain change here. Whenever the values nearby x, whatever the values you are going to put, the domain, so whatever the change nearby x takes place, correspondingly y changes, and the nature of the change of the function y, that is studied in detail in this section calculus here. So anyhow, there is a great contribution by these two mathematicians here, great mathematicians. One is Sir Isaac Newton and then G.W. Lagrange. In the 16th century, they have developed this calculus unit, and this is a very, very interesting and important branch in mathematics here. Calculus is the foundation, very, very important for your higher studies, for your engineering, space study, and many more fields. In many more fields, this is the base, this is the fundamental here. And for first PUC, you are mainly concerned with the study of concept of limits and very, very basic concepts of derivatives. Only introduction to derivatives is there here. So more of the concepts will be studied in the second PUC. Anyhow, let me continue the first concept, that is what limits and continuity here. Limits. First of all, let us study the concept of the limit of a function here. So before knowing the meaning of the limit of the function, let me make you clear one symbolic representation, that is what tends to. This is in ordinary sense, it may have a different meaning, but in the language of mathematics, this tends to, in particularly in the language of limits, it has a specific meaning here. This tends to word we symbolically represent with an arrow here in this manner here. What does it mean? Let me clarify this with the help of an example. Let me take into consideration 4.9 here. So one value I have written. One more value I would like to write below this, just observe here, 4.99 here. And then one more value, 4.999 I have written, 4.9999. In this manner I can continue here. Okay. Suppose you take this as the value of x here. Now take it as x. See, x takes the values 4.9, then 4.99, 4.999, so on. This sequence is continued here. If you observe this pattern, this x value is approaching towards a particular value. What's that? Can you judge, anybody? Here it is approaching towards a particular one value, one constant. Can you tell me? 5. Yes, very good. It is approaching towards what here? 5. See, symbolically we write it as x tends to. See here, x tends to 5. X tends to 5 we write here. Symbolically we write it as x tends to 5 here. X tends to 5. Means, see, x tends to 5. See, x is moving very nearer and nearer to 5. Okay, approaching but not achieving, not exactly equal to 5. It is approaching very, very near. it is approaching to 5 but not achieving exactly 5. So this is sense of understanding you keep in your mind with respect to tends to here, because often and often at every step we are using the symbol tends to. We say x tends to a, x tends to b, x tends to pi by 2, x tends to 0, theta tends to 0, like this. So this is a everyday routine work with the concept of limits here. So that's why I made it clear this. Okay. Now let us discuss the concept of limit of a function. Let me discuss the limit of a function by taking a simple example here. In a formal way I would like to discuss here, not in more theoretical way here, a practical way of I will try to convince you the practical way of the concept of limits here. So the limit of a function, what is the concept? What do you mean by the limit of a function here? So for the sake of convenience I have taken a rational function y equal to f of x, which is equal to x square minus 9 divided by x minus 3 here. So this is a rational function here. See, at x is equal to 3, if you observe this carefully, the y becomes f of 0, which is equal to what we will get 3 to the power 2 minus 9 divided by 3 minus 3 here. On simplification we will be getting 9 minus 9 divided by 3 minus 3. So you will be getting 0 divided by 0. See, by mistakenly you don't write 0 by 0 is equal to 0. It is not possible here. In the language of limits, in the language of mathematics, not only limits, this is meaningless. We say this as indeterminate form here. So many forms are there here in mathematics, not only 0 by 0, such as infinity upon infinity, infinity minus infinity. Many are there. I will separately discuss that, but this 0 upon 0 is an indeterminate form, not possible to calculate. It has no meaning here in the language of mathematics. So the function is attaining indeterminate form at x is equal to 3. Let me check the value of this function in the neighborhood of 3, means side by side, very close to 3 on left side and very close to 3 on right side here. That means when x is less than 3 and when x is greater than 3, it means combiningly what we can say, when x is approaching to 3, it means when x is not equal to 0, when x is not equal to exactly 3. What about the value of this function? That is, when x is not equal to 3, see, we can visualize this situation in this manner here. When x is not equal to 3, this fx can be written as x square minus 9 is there, that can be written as x square minus 3 square divided by x minus 3. So by factorization you will get it as x plus 3 into x minus 3. Very simple. You can realize this, no need of any more explanation here. X minus 3 and x minus 3 can be cancelled and remains what? X plus 3 remains. So when x is not equal to 3, the value of fx becomes x plus 3. Now let me take some values in this domain, that is in the neighborhood of 3. That is when x is less than 3 and when x is greater than 3. See, x less than 3 values I would like to assign. Say for example 2.9 here. So what about y here? See, recall this, fx is equal to or y is equal to what we got here, x plus 3 we got, x plus 3. If you substitute 2.9 plus 3 becomes how much, can you tell me? If you take x is equal to 2.9, 2.9 plus 3 leads to how much?
5.9.
5.9, okay. And take the difference of the absolute value of fx and 6. 6 and 5.9 difference is 0.1 here, 0.1. Absolute value you need to take, positive value you need to take here. And next still nearer I would like to move to 3, less than 3 but very near here, still near. 2.99 if you take, this becomes what? Can you respond? Y becomes what? 5.99 it becomes here. So the difference will be 0.01. Do you agree with this? 0.01 here it is. And then next 2.999 I would like to take. Then this becomes 5.999. So definitely it is 0.001. Similarly, if you take 4 nines on the decimal place, this becomes 5.999, again it is 0.0001 here. This is sequence you continue here. So in the same manner you can continue this difference will be continued. So I have taken in the neighborhood of 3 the values which are close to 3 but less than 3 here. In the next table, in the second table, I would like to take the values slightly greater than 3. Say for example, 3.1 I would like to take here, 3.1. If you take 3.1, y equal to fx, 3.1 plus 3 it becomes 6.1, very easy to judge here. And then 3.1 plus 3s, 6.1 it is. So the difference is again 0.1 here. Fx and 6 difference is 0.1. Now observe here. Okay, 3.01 I would like to take. Still nearer, still closer I would like to move. 3.01. Then it becomes 6.01. So the difference is 0.1. 3.001 if you take, it becomes 6.001. 0.01 here it is. Sorry, 1 0 extra and then 1. Next 3.0001 you take, then it becomes 6.0001 because y equal to x plus 3 here. X value is 3.0001 plus 3. So it becomes 6.0001. So the difference is 0.0001 here. In this manner we can continue here. See, if you observe these two values, say this as table 1 and then table 2. From these two tables, what we are conclude here? Observe carefully here. See, in the neighborhood of 3, we have taken these values. Please try to understand the concept here. Please try to understand the concept. A very interesting concept is there if you understand. Otherwise, at the same time, difficult aspect also here it is. See, if you take into consideration, say this as 3 here. This is the point 3 here. And then x is approaching towards 3 from left side here in the first table, and then x is approaching towards 3 from right side in the second table here. In both the cases, what we observe here, please carefully observe here, when x is very close to, when x is very close to 3, that is either from left side or from right side, from both the sides, left and right, both the sides. Table is very clear here. When x is very close to 3, you observe carefully the value of y, the value of f of x. It is approaching towards what? Please, can you respond? Both the tables you observe. 5.9, 5.99, so on, 5.9999. Here, 6.1, 6.01, 6.001, 6.0001, so on. If you observe, fx value is approaching to a certain value. What's that value? Yes, very good. When x is very close to 3, then fx is very close. Very close means nearer and nearer. Close to 6 here. This is what our observation. Here we are, x is approaching 3 but not exactly reaching. Approaching but not achieving. Not achieving here. See, x is very close to 3, then fx is very close to 6 here. X is nearer and nearer to 3. When x is moving nearer and nearer to 3, the value of fx means y is moving nearer and nearer to 6 here. So this is what the funda what we have observed in this discussion here. Let me use to define the concept of limit this discussion here. See, let us observe some content I have taken already. Please concentrate here. This behavior of the function fx equal to x square minus 9 divided by x minus 3 in the neighborhood, side by side, less than 3 and then greater than 3, is what we mean by the limit of the function fx equal to x square minus 9 divided by x minus 3 is 6 as x tends to 3. That means the limit of this function, see, the limit of this function as x tends to 3 means when x is approaching to 3, then the value of limit of this function, the limit of this function is found to be what here? 6. The value of the limit of the function is 6. When it is becoming 6, when x is approaching to 3, the value of the limit of the function fx is equal to 6, we say here. See, symbolically we write LIM. In some text LT we write LT also. Sometimes small l and small t also chosen here. And LIM, it is convenient to write LIM here. Limit, we read it as limit, but LIM is the symbol. X tends to 3, below that LIM you need to write here. Fx is equal to limit x tends to 3, x square minus 9 divided by x minus 3. That fx is defined in this manner as a rational function here. It is equal to 3. We have written for the calculation purpose in the language of mathematics, we have written equal to 6. But basically it is not exactly equal to 6. It is very nearer and nearer to 6 here. So this is what the idea here. So we read as the limit of fx as x tends to 3 is 6 here. So this is what the concept of limit explained with the help of a particular example here. Likewise, we can take many more examples. But I would like to generalize this. I would like to generalize this concept to define the concept of limit here. See, in what manner we can generalize it here? A function, you take a general function y equal to fx. This is a function here. This is said to tend to the limit. See, the function is tending to the limit L here. That means in the previous example, x square minus 9 divided by x minus 3 is tending to 6. 6 in place of 6, you imagine L here. A function fx is said to tend to the limit L as x tends to a. This is the tending limit. If the difference between the value of the function fx and L becomes smaller and smaller whenever the difference between the values of x and a is smaller and smaller. This is well understood with the help of this table. Here, let us come to this example here. This table here. Observe the value of the difference of fx and L here. So this is what your L in this case, L in this case here. So this is fx here. Fx minus L value, it is becoming smaller and smaller. Whenever the difference between x and a, is becoming smaller and smaller. You observe here the value of x. The value of x is tending to 3. Okay, x and a, x value and a value here. So that difference is becoming smaller and smaller. Whenever the difference between x and a is becoming smaller and smaller, at that time it is observed that the difference between fx and L is becoming smaller and smaller. So this is what the visualization. Please concentrate here. That itself, in other words, the same thing, the function fx takes the values nearer and nearer to L whenever the variable x takes the values nearer and nearer to the value a, then we say that fx tends to L as x tends to a, and we denote symbolically by the symbol limit x tends to a fx is equal to L here. See, the value of limit x tends to a fx is equal to L. How do you visualize this situation here? The difference between fx and L is becoming smaller and smaller as the difference between x and a is becoming smaller and smaller here. So this is what the symbolic representation, we read it as limit x tends to a fx is equal to L here. So this is what the formal definition. Now let me discuss one more very important and interesting fundamental concept here. Left hand limit and then right hand limit. Left hand limit, this is also represented shortly as LHL, and then one more is RHL here, right hand limit. Left hand limit and then right hand limit here. Let us try to understand the concept of left hand limit here. See, if the function fx is said to tend to the limit, see, the function fx is said to tend to the limit, you say L1 as x tends to a from the values which are less than a. Observe this, this is a number line, a is the point on the number line, x tending towards what here a, but from left side here, from left hand side, LH, left hand side here. Actually it is left hand side, x is tending towards the value from left side here. That is on the number line, x is tending to a from left side of a as shown in the figure. You observe this. This limit is called the left hand limit of the function and is denoted by limit, see here, limit x is tending to the value slightly less than a. You can't write many more values. In the previous example, 2.9, 2.99, so on, many more values we can take. That always summarize in this manner. X tends to a lesser value, that's why a minus symbol is written over this. X tends to a minus fx. This is what the symbolic representation of left hand limit. So this is equal to what here? L1. This is left hand limit. LHL is equal to what here? Limit x tends to a minus fx is equal to L1. Please observe this. X is approaching a from left hand side. Here x is approaching to a from which side here? From left hand side in case of the left hand limit. The same funda is to be applicable to the right hand limit. What's that? You see here again a number line. X is approaching from right hand side. Where it is approaching? It is approaching towards what here? Okay, when x is approaching to a point A from right hand side, then that's called the right hand limit. See, it is approaching to, say it is said to tend to the limit L2. Then we write it as right hand limit RHL is equal to limit x tends to a. The point is same here and the value a, but over that we write it as plus from right side greater than a. A plus means what does it mean? X is tending to a plus means what here? X is tending to the value from the value slightly greater than x is slightly greater than a. X greater than a. X. Yes, a plus means the value of x is greater than a. If you take in the previous example, 3 is the point here. Right hand side, this is right hand side, and then this is left hand side here. So that is what the idea here. See, a plus means x value is greater than a. So this is what fx, and then this is equal to what here? L2. We represent it as L2 here. So this is what the concept of the right hand limit. This is what the right hand limit. Please concentrate here. If the function fx tends to the value limit L2 as x tends to a from the values which are greater than a, that is on the number line, x is tending to a from right side of a here. See, x is approaching from right side, here. So this is what the idea regarding the we can say here, right hand limit here. So this is the concept of right hand limit. And one more very important thing you remember, for a function limit x tends to a f of x to exist here, this left hand limit and right hand limit must be equal here. So whenever, please concentrate here, what you need to remember, when limit x tends to a f x exists, when this value exists here it is compulsory. Limit x tends to a minus means the value of x is slightly less than a. Fx, that means left hand limit, this must be equal to limit x tends to a, but it is a plus right hand limit, a plus fx. These two must be equal here. Then only the limit exists. Limit x tends to a exists here. So whenever the limit of the function exists, you remember perfectly left hand limit is equal to what here? Right hand limit. So this is what the concept behind this. I hope you followed the concept of left hand limit and right hand limit. In the language of mathematics, in the while defining the limit, there must be a tending value. X tends to something, either a, 0, 1, 2, 3 something. Left hand limit means left side of that point here. Right hand limit means the right side of that point. So this is what the funda behind this. I hope you followed. Let me continue the next concept. Let us see what's that. Indeterminate forms here. Now let me take into consideration the concept of indeterminate forms here. Actually, there are 7 indeterminate forms here as for my information is concerned here. Please concentrate here. Some are very familiar for us. Previously I have discussed 0 by 0. 0 divided by 0, this is indeterminate form. Infinity upon infinity is also indeterminate form. We don't say this is equal to 1. 0, 0 cancels, it becomes 0. Infinity, infinity cancels, it becomes 1. It is not possible like that. So infinity minus infinity, this is also an indeterminate form here. Other than that, infinity into 0, this is also not equal to 0. You may confuse infinity into 0 is equal to 0, but it is not possible. 0 raised to 0, infinity raised to 0, 0 to the power 0, infinity to the power 0. Observe here, since from your primary level the teachers have been mugged up, anything raised to 0 is 1, anything raised to 0 is 1, but it is not so, because to that at that level it is customary, every teacher will guide like that, but 0 raised to 0 is meaningless, it is indeterminate, it is not possible here. So infinity raised to 0, similarly 1 raised to infinity also, will be surprised here. 1 into 1 into 1 into any number of 1, it will give 1 here. You will judge very easily, but it's not so. It's also not defined. So 1 to the power infinity, this is also an indeterminate form. There are actually 7 forms, 1, 2, 3, 4, 5, 6, 7. Okay. So these are the indeterminate forms in mathematics here. And why I have introduced all these, the concept of limits, limit concept helps us, this limit concept helps us to deal with these functions, these forms, with these indeterminate forms. So whenever, please listen to me, whenever the function is leading to an indeterminate form, we can tackle that function, can evaluate that function in the neighborhood of that point where it leads to, that point which is responsible for that function to become an indeterminate form here. So in the neighborhood, we take the values and then we can evaluate it by applying the concept of limit here. So this is what the main use of the limit of the function here. So these are the indeterminate forms. To deal with the functions which lead to indeterminate form, we apply the knowledge of limits and solve the functions.